Hi, again welcome to International Institute of Non-Destructive Testing. Today also we are going to discuss on magnetic particle testing, and we are discussing on current. Listen on current. There are three types of current we are using in magnetic particle testing. One is AC current, second is HWDC current, and third one is DC current. Okay, so here we are going to do the detailed study about the current. Though, so alternating current is the most widely used power source for conducting magnetic particle testing. AC can be readily converted to the low voltage used in magnetic particle inspection by the use of transformer. AC has little penetrating power and provide the best detection of surface discontinuities. It is not effective for subsurface discontinuities. See, this is the waveform of AC is flowing from positive to negative, again negative. So the waveform current is flowing from positive to negative and negative to positive. See, this is the AC current. Now here this negative cycle we remove with the help of rectifier, and that's why the rectified AC current, this waveform is for rectified AC. Now this negative cycle is converted into positive cycle, so we are getting here direct current, continuous direct current. Here is this is the single phase, this also single phase, but here three phase, we are adding two more phase, so the total current is three phase current. Where if you want more current because of the requirement of big current uh, requirement, so we have to use three phase current as well we can use. So this direct current, how we are here, this is the rectifier. With the help of rectifier we are removing this negative cycle and we are getting HWDC output. So in HWDC output, in simple way, the current is flowing, then there is some interval, no current is flowing, again there is some interval which where current is flowing. So this is the pattern. Now hysteresis loop means just you see a thing on this job. So this graph representing vertical axis is flux density and horizontal axis is magnetizing force, and this is the plus side of graph and this is negative side. This is again plus side, this is also negative side. Now you know when you are applying current to ferromagnetic material, the magnetic field generated in the specimen. Now the amount of magnetic field generated in the specimen depends on amount of current, number one, and second, permeability of material. So permeability of material. So if high permeability, then magnetic field will be generated, amount will be high. If less permeability, then amount of magnetic field will be less. Even if you are increasing more current, the magnetic field will never increase. So now look at here. Suppose if you are increasing the current, magnetic field is again increased here. And suppose, for example, this current amount is, for example, 800 amps. Now this current amount is 800 amps. So after 800 amperes, even if you are trying to increase current, so there is no change in magnetic field. So magnetic field remains constant. So that point is known as saturation point. Saturation point means you are increasing current, magnetic field will be increased, but that is up to certain limit. That after that limit, even if you are increasing the current, then magnetic field will never increase. That point is known as saturation point. Now saturation point is your highest magnetic field while current is flowing. Then we can say this is the point, for example, B dash 1. Now you know the AC current is flowing from positive to negative, negative to positive. Now here suppose when current is flowing at this point, you will get this point. After that your current is flowing here. huh? So in this point, in this particular point, there is no current flowing in the specimen. There is zero current in the specimen. So there is this magnetic field is when we are getting when current is flowing. Now there is no current flowing means this field will be reduced. So this is the residual magnetic field. Residual magnetic field means if you are removing the magnetizing current, magnetizing force, the sum of the field is remaining in the material. The amount of that field depends upon retentivity. If retentivity of material is high, then amount will be high. Residual amount will be high. If retentivity of material is less, then a residual amount is less. So now you are getting this point. Now again this current is flowing from this point to negative point, so we are getting this curve again on the negative side, saturation point. The field is same, but the sign is negative. So again, current is going positive to, sorry, negative to positive. That's why this curve again going here. Here, current is not flowing means this point. and after that current is going here, so this this will go here again. So this pattern is known as hysteresis loop. It is a graphical representation between current and magnetic flux density, retentivity, coercivity. So these things we are getting through this hysteresis loop, and this hysteresis loop we can create only for AC current, because AC current is only flowing from positive to negative. But in case of HWDC or direct current, we can't do this hysteresis loop, because the current is flowing only positive side in both cases. Okay, so this is the hysteresis loop, and we are going to see little bit detail in next PPTs. Now see, this is the point. So this is the residual magnetism, and as the magnetizing force is reduced to zero, then flux density slowly drops until the magnetizing force is zero. The ability of steel to retain a certain amount of residual magnetism is called as retentivity, as shown point 0.02 B. This is the retentivity. This is actually residual magnetic field, but this residual magnetic field because of retentivity properties of material. Uh, now see, now this is the coercive force. If you want to reduce this residual magnetic field, then we have to apply this reverse magnetizing force. So reverse magnetizing force means is a coercive force is the reverse magnetizing force required to remove the residual magnetic field, residual magnetic field or magnetism from the material as shown above, means this residual magnetic field. Then hardened steel would require a stronger reverse magnetizing force to remove the residual magnetism. Now this is you see, then as reference magnetizing force is increased beyond point C, the flux density increases to the saturation point in the reverse direction at point D. Where is point D? Point D is here. Okay, so that means your current is going to negative side, you will get negative side saturation point. If current is going positive side, you will get this positive point, saturation point. One thing here you remember, all of you please remember, this is saturation point. Now this saturation point, it depends upon permeability of material. If material is having high permeability, this point will be increased or increased. If material having less permeability, then this point will be reduced. Now this is the residual magnetic field. This depends upon retentivity of material. If retentivity of material is high, then more amount of residual magnetic field is there. If retentivity of material is less, then less amount of magnetic field is there. Now this is the reverse magnetizing force necessary to remove this residual magnetic field. If residual magnetic field is less, then reverse magnetizing force is less. Less reverse magnetizing is force required to remove this residual magnetic field, and this reverse magnetizing force we can say that is coercive force. Now see this, look at here, this is less saturation point here. Less saturation point means this material is hard, means low permeability. Now see here, this is again here, this residual magnetic field is high, and this, if this field is high, then this reverse magnetizing force required high. To coercive force means the reverse magnetizing force necessary to remove this residual magnetic field. Okay, so this if reverse magnetizing force high means this area is wider, your hysteresis loop will be wider, not shallow, it is wider. So it is thick, not thin. In case of low carbon steel, this point, this width you will get less, and the saturation will be high. We will discuss in next PPT. But before that, we can see here hard steel would have the following qualities or properties. Low permeability. If material having high carbon or material is hard steel, then permeability is low. So low permeability means hard to magnetize. High retentivity retains a strong residual magnetic field. If retentivity is more, then if you are removing current, then also there is high residual magnetic field. And if high residual magnetic field is there, then we have to remove that field. Then we need more reverse magnetizing force necessary to remove this residual magnetism. Is known as high coercive force, and that high coercive force is necessary, requires a high reverse magnetizing force to remove the residual magnetism. Then high reluctance, high resistance to magnetizing force, high residual magnetism retains a strong residual magnetic field. Now see here carefully. If if material is hard, hard in the sense hard to magnetization, that means low permeability. If permeability is low, then it will get take more time for magnetization. Even magnetic field is less. And once magnetized, it will retain for long time. That's why retentivity is high. If permeability is low, then retentivity is high. If high retentivity means it will preserve more amount of residual magnetic field. And suppose if you want to remove that residual magnetizing field, then we have to apply more reverse magnetizing force. Then we can say that is high corrosive force. And high reluctance means if you are if suppose material is hard to magnetization, that means more reluctance. And if it is hard to magnetize, then it will sustain more amount of residual magnetic field. uh, so we can say high residual magnetization, magnetism or magnetization, both are same. Okay, it retains a strong residual magnetic field. Now you see, look out here, this is very thin hysteresis loop and saturation is high, means high permeable material. So high permeability of material basically, if suppose we can say low carbon steel is high permeable material, permeability is high. So based on this pattern of hysteresis loop, we need to identify which is high permeable material or which is less permeability material. So we can understand with the help of this graphical representation. So, soft or low carbon steel would have the following qualities: high permeability, Ag2 magnetized, low retentivity, retain a weak residual magnetic field, low corrosive force, require a low reverse magnetizing force to remove the residual magnetism, low reluctance, low resistance to magnetizing force, and low residual magnetism, retain a weak residual magnetic field. Means if permeability is high, that means reluctance is low because it is easily magnetized. And if reluctance is low, then retentivity also less. Easily it will leave the field. Leave the magnetic field, leaving the magnetic field. So, and if less residual magnetism, then the less reverse magnetizing force necessary to remove the magnetic field. So, low corrosive force means here, if you understanding clearly, if permeability is high, then other all properties will be low. If permeability is low, then other all properties will be high. Then, if suppose if you have any doubt or if you need further assistance or so please, we are happy to assist you. So please feel free to write us to indtpune@gmail.com, or you can call us directly +919004513517. So you will we will happy to provide you the detailed information about it. Thank you very much.